By the middle of the 19th century, the most ambitious machine ever conceived was a ghost. It had been designed, it had been drawn in exquisite, painstaking detail. It had been imagined by its creator, Charles Babbage, as a mechanical brain that could perform any calculation imaginable. But it did not exist. It did not run. Babbage's analytical engine remained a grand, unfinished symphony of brass and steel, trapped in the space between vision and reality. To most of the world, it was an epic failure, a colossal waste of time and money. A machine that could not operate was dismissed as an eccentric's fantasy, a theoretical curiosity, an intellectual indulgence. Babbage himself grew frustrated, battling with engineers, politicians, and the very limits of Victorian technology. He saw his dream as a collection of gears, levers, and steam-powered pistons, physical marvel that refused to come to life. The world saw a pile of inert metal and a broken promise. But one person saw something entirely different, someone who looked past the rust and the silence. That person was Ada Lovelace. Ada was the daughter of the famous poet Lord Byron, but her mind was drawn not to romantic verses, but to the rigorous beauty of mathematics. She had been Babbage's student, his collaborator, his intellectual confidant. And when she looked at the silent, unbuilt analytical engine, she did not approach it as an engineer of metal or steam. She approached it as a poet of symbols. Where others saw gears and levers, Ada saw relationships. Where others saw a tangled mess of mechanical parts, she saw a logical structure. Where Babbage and his contemporaries saw a machine for calculating numbers, Ada saw a machine capable of so much more. She saw potential. Ada understood something so radical, so profoundly ahead of its time, that it would take another century for the world to catch up. She realized the machine was not important simply because it could calculate. It was important because it could follow instructions. It could execute a plan. In an era when machines were built to amplify physical labor, to spin cotton, to pump water, to power locomotives, Ada imagined a machine that could manipulate ideas. She grasped a fundamental concept that is the very bedrock of our digital world today. She recognized that numbers were merely representations. They were symbols. And if they could stand for quantities, they could just as easily stand for other symbols, for musical notes, for letters of the alphabet, for logical concepts. This was a breathtaking leap of imagination. If numbers could represent anything, then a machine that processed numbers could process more than just mathematics. It could handle logic, it could compose music, it could create art. It could weave algebraic patterns just as the jacquard loom wove flowers and leaves into fabric. She called it the science of operations. Ada wasn't fascinated by what the machine was, a complex, unrealized calculator. She was fascinated by what it could become. She saw a general-purpose device, capable of being programmed to perform an infinite variety of tasks, limited only by the creativity of the person instructing it. While the physical analytical engine remained silent and incomplete, Ada began writing something truly unprecedented. She took a complex mathematical problem, an algorithm for calculating something called Bernoulli numbers, and translated it into a series of steps the analytical engine could perform. She was writing instructions, but these were not instructions for building the machine. They were instructions for using it. She laid out step-by-step sequences, logical operations, and even conditional processes. This happens, then do that. She described how the machine would have to loop back on itself, repeating a series of actions. She was, in essence, creating a detailed plan for a machine that didn't even exist. What she was creating did not depend on the machine being finished. It existed independently as a pure intellectual construct. Ada was writing a method, a language, a way to tell a machine what to do, even if that machine could not yet respond. In a world obsessed with physical invention, with steamships and telegraph, Ada invented something invisible, a process, a set of logical rules. In her detailed notes, published in 1843, she outlined a concept that would one day be known by a simple, powerful name, software. And in doing so, she crossed a boundary that no one else had even noticed was there. She separated the physical hardware of a machine from the abstract, logical instructions that told it what to do. She was the first person to see that the real power wasn't in the gears, but in the instructions that controlled them. She was the world's first computer programmer. For decades, her work was largely forgotten. A footnote in the story of Babbage's magnificent failure, an analytical engine was never built. Babbage died, disappointed. Ada Lovelace died young. At just 36, her contributions misunderstood and unappreciated. But her vision did not die. A century later, when the pioneers of the electronic age, people like Alan Turing, began building the first true computers, they were, in many ways, finally building Ada Lovelace's machine. They rediscovered her work and recognized its genius. They saw that she had not just been commenting on Babbage's invention, she had understood its potential more deeply than Babbage himself. Today, every time you use a smartphone, every time you browse the internet, every time you interact with an app, you are living in the world that Ada Lovelace first imagined. A world where machines don't just calculate, but create, communicate, and connect. A world driven not just by hardware, but by the elegant, invisible power of software. The story of Ada Lovelace is a powerful reminder that true innovation is always about building a bigger, faster machine. Sometimes, it's about seeing the world differently. It's about finding the poetry in the logic, the art in the algorithm, and the boundless potential hidden within a silent machine. She was the enchantress of numbers who looked at a ghost and saw the future. But she was so much more. She was a visionary, a mathematician, and arguably the world's very first computer programmer. Imagine Victorian London, a world of steam engines, gas lamps, and horse-drawn carriages. In this era, a man named Charles Babbage, a genius inventor, was dreaming of a machine he called the analytical engine. This wasn't just a calculator. It was a mechanical computer designed to solve complex mathematical problems automatically. It was a revolutionary concept, a machine of gears and levers that could, in theory, think with numbers. Babbage was a brilliant hardware guy, but he was so focused on building his machine that he almost missed its true potential. That's where Ada Lovelace comes in. She met Babbage and was instantly captivated by his invention. But unlike others who saw it as just a powerful calculator, Ada saw something deeper. She saw a future that no one else could even imagine. She translated a paper about the analytical engine from Italian into English, but she didn't just translate it. She added her own extensive notes, which ended up being 3 times longer than the original article. And in those notes, she laid out the very foundations of modern computing. This is where things get truly mind-blowing. Ada's most extraordinary insight was also the most unsettling one. She realized that the analytical engine didn't need to understand what it was doing. It didn't need to know what a number meant. It only needed to be able to manipulate symbols according to a set of rules. Think about that for a second. Meaning wasn't required, only rules. If the instructions were precise enough, a machine could perform incredibly complex operations without any comprehension at all. This was a radical idea. It separated the concept of intelligence from the act of execution. The machine didn't need to think. It just needed to obey logic. To prove her point, Ada described step by step how the analytical engine could be programmed to calculate a complex sequence of numbers called Bernoulli numbers. She laid out each operation in a structured, logical sequence. Inputs, processes, outputs. This wasn't just math anymore. This was the architecture of computation itself. What Ada wrote is now recognized by historians as the world's first algorithm designed specifically for a machine. It was the very first computer program, and here's the craziest part: there was no computer. The analytical engine was never fully built in her lifetime, so the program existed before the machine. The logic existed before the execution. Software came before hardware. This complete inversion of how we think about technology was revolutionary. It suggested that the true power of machines did not lie in their physical strength or their mechanical complexity. It lay in the invisible instructions that guided them, the software. But Ada didn't stop there. She also saw the limitations. She warned that machines could only do what we tell them to do. They have no originality, no creativity, no intuition, no real understanding. She imagined that a machine could compose music or create art, but only if the rules for harmony and composition were fed into it first. The machine isn't the artist. It's just a very sophisticated tool for the artist. This distinction is so important. Ada wasn't imagining some kind of sci-fi artificial intelligence that would replace humanity. She was defining its boundaries. She saw both the incredible promise and the potential danger. Machines could extend our human capabilities in unimaginable ways, but they could never, ever replace human insight and creativity. Her vision was subtle, balanced, and so far ahead of its time, it's staggering. Tragically, Ada Lovelace died young, at just 36. After her death, her groundbreaking ideas were largely forgotten. Babbage's analytical engine remained a dream on paper, and the world moved on. But the logic didn't disappear. It just waited. It hibernated for more than a century. Then, in the mid-20th century, the first electronic computers were built. Men like Alan Turing and John von Neumann were developing the theoretical basis for these new machines, and as they did, they independently rediscovered the very same principles that Ada Lovelace had laid out 100 years earlier. They found their way back to her structure: programs, instructions, algorithms. That invisible layer of logic that makes a machine useful. Today, every single line of code that runs our world on your phone, in the cloud, in your car is an echo of Ada Lovelace's fundamental insight that machines don't act because they think, but because they are told what to do. The first programmer never saw or touched a computer. She wrote code for a machine that didn't even exist. And in doing so, she didn't just predict the future. She defined the very logic that would make our modern world possible. Ada Lovelace's legacy isn't just in a programming language named after her. It's in the very DNA of every piece of technology we use today. It's a powerful reminder that sometimes the most revolutionary ideas come not from building the machine, but from understanding what it can become. Thanks so much for watching. If you found this story as fascinating as I do, please hit that like button and subscribe for more deep dives into the history of science and technology. See you in the next video.